Let's do one more example for this section. For this problem, we're going to have 5 kilograms of nitrogen. It's undergoing a process from a pressure of 5 bar and a temperature of 400 Kelvin to a pressure of 2 bar and a temperature of 500 Kelvin. So we are decreasing pressure but increasing temperature. We're going to assume an ideal gas and we're going to find the change in entropy with constant specific heat. That's evaluated at 450 Kelvin. And then we'll use variable specific heat. So this will show you how to use those values in the ideal gas table, which will be a good thing to know how to do. First thing we're going to do, part A here, we got to go to our table. You're going to go to table A20 if you're using the Moran tables, and this will be the ideal gas table for the specific heats for nitrogen. All right, it's got other substances. We're obviously going to focus on this one. And temperature is on this left side. Our temperature is at 450, so here is this. And you can see we've got CP right here and CV. Let's write those values down. Actually, not those, that's air. Let's actually use the right substance, which means we'll be over here. All right, so 1.049 and 0.752. So table A20, CP is 1.049. It's kilojoule per kilogram Kelvin. CV is 0.752 kilojoule per kilogram Kelvin. Now we've got that. What we're wanting to do, remember, is find the change in entropy. So let's write an equation for that. So S2 minus S1 equals CP times the natural log of T2 over T1 minus R times the natural log of P2 over P1. And we can use this equation because we said we had constant specific heats. So we were able to find the values in the table. Remember, R is equal to R bar over molecular weight. So let's figure out what that is. So that's 8.314 over 28.01. Units will be kilojoule per kilogram Kelvin. Now that we've got R, we can plug in our values. So S2 minus S1 is going to be 1.049 kilojoule kilogram Kelvin times the natural log. Temperature 2 is going to be 500 Kelvin. Put that over T1, which is 400. Notice Kelvins go away. Then we're going to have our R number. I don't have the actual value here, so we're going to write the R bar over M. Got 8.314 over 28.01. It's kilojoule per kilogram Kelvin, multiplied by the natural log of P2 over P1. Final pressure was 2, initial pressure was 5. So we got 2 over 5. Notice the bar cancels. So now we've got that. So far, so good. If you look, our units all work out. Both terms are in the same units, so that's good. Now go ahead and do your calculations, and you're going to get 0.506 kilojoules per kilogram Kelvin. Now, are we done? Is that what the problem asked for? Nope. Because it wanted entropy to be in kilojoules per Kelvin. We've got this kilogram here. We got to get rid of this. How are we going to do that? That's right, we're going to multiply by the mass. Remember, these are specific entropy. We don't want that because that's not what it asked for. So our entropy is going to be S2 minus S1. Those are the capital S's. It's going to equal the mass, which was 5 kilograms, times this 0.506 value. Now kilograms is gone, and that'll give us 2.53 kilojoules per kilogram. So that's going to equal our change in entropy. All right, so perfect. Done with that one. Now I got to go to part B. So part B, we have variable specific heats. If you have variable specific heats, you're going to use this equation. This will be the one that uses the S degree term. So S2 minus S1 equals S degree at T2 minus S degree at T1 minus R times the natural log of P2 over P1. And remember, these come from the table. Now the table we're going to use is going to be this one. All right, so A23, this one has nitrogen in it, and it's for ideal gas. So we've got that. All right. Now, keeping that in mind, we're going to find these two values in the table, so all we really need is the temperature. For T2, we're at 500 Kelvin. Now, if you look in this table, let's look at this. It's hard to see because it's so small, but notice all these terms have the bar over it. We've talked about this before when we did ideal gas. This one has a bar over it too. The bar indicates, if we look up here at the units, that we've got kilomole in the denominator. So it doesn't have the kilogram, it's got kilomoles, so we need to make sure we take care of that. Let's write out that value though. So at 500 Kelvin, you get a value for S of 206.63. That's kilojoule per kilomole Kelvin. And we'll take care of the kilomole in just a second. Let's do the same thing at T1. At T1, we're at 400 Kelvin. So just go on the table, go to 400, and then go all the way over to here. There you go. Actually, these are temperatures too. So you get the 200.071. And that's kilojoule per kilomole Kelvin. Now we're ready to use this equation. And when we use the equation, we'll take care of the kilomole issue. So we're going to have S2 minus S1. It's going to be this value minus this value. So 206.63 minus 200.071. Those are both kilojoule per kilomole Kelvin. Now to get rid of kilomole, what should we do? We're going to divide by M. So that's 2801 kilograms per kilomole. So that's molecular weight. That comes from table A1. That takes care of this part. Now we have this last term here. R is going to be the, we did it up here, it's the 8.314 over 28.01. So let's put that in there. And kilojoule per kilogram Kelvin, multiply that by the natural log of P2 over P1. So that's 2 bar over 5 bar. Bars go away. And again, kilomole cancels here. So the units are all the same for each of the terms. We get kilojoule per kilogram Kelvin. That's what we wanted. So now you can go through and solve. So what you'll get is a change in entropy of 0.5062. That's kilojoule per kilogram Kelvin. Now, again, notice we have kilogram down here. That means this is specific entropy. These are little s's, remember. Specific entropy, we want just entropy. That means we need to multiply by mass. So we're going to have 5 kilograms, and we get 0.5062 kilojoule per kilogram Kelvin. That gets rid of kilograms. So we get 2.531 kilojoules per Kelvin. All right. So if you notice, you got about the same answer using either of those methods. All right, but this is how you're going to do it, how you'll use this table if you have variable specific heat. You just look these up plug them into that equation. Not too challenging. But notice here you got the same values about. All right, so I will see you guys next time. Thanks.